All right, welcome to your first honors pre-calculus video. We're going to go review and go over one-to-one functions and inverse functions. So we're going to start off with just recalling what the definition of a function is and also remembering some function notation. So the definition of a function is a relation in which each member of the domain maps to exactly one member in the range. Okay, so we use like mapping diagrams to kind of demonstrate this when you first learn it. So like if I have a set of members, we'll call it the domain, we put this like oval looking thing. I'm going to put people in there like Jason and James. I'm going to make this a little bigger so I can get some more elements in my domain. Scott, Christina. Okay, so we've got some members, some people here in our domain. And then we're going to make a range. We'll have things like A positive, A negative, O negative. All right, so those are going to be blood types. So blood type is an example of a function. In other words, like Jason could map to A positive, and then Jason cannot map to O negative. That would mean it's not a function. If any member of the domain maps to two different members in the range, that is not exactly one, right? It needs to be exactly one. 2 is not exactly 1. All right, so that would not be a function. And we know that. I can only have, or well, Jason's me. I can only have one blood type. James may also map to the same blood type as me. We might both be blood type A. So that is still a function because James maps to exactly 1. Jason maps to exactly 1. So this is still a function even though they map to the same range member. Maybe Scott maps to A negative and Christina maps to O negative. All right, so we'll call that function, that's blood type. I'll call it B of X or something. So we use that language maps to, okay, and that's a mapping diagram. Forgot the I there, snuck it in. All right, so that's a mapping diagram. A good example is our blood type. Let's go over some function notation stuff. Let's recall some of this. So if we look at like what we remember, we have the mapping, but we also use this notation like f of x, okay? And I'm going to use like x sub 1, x sub 2 to denote different domain members. So, for instance, the first thing with function notation, like we could say, I'll just call this number 1. X sub 1 is a domain member. X sub 2 is another or a different domain member. You could think of them as, instead of domain member, right, we could think of it as, whoops, not output. Domain is input. We've used for functions, you've said like input, the thing you put into the function, or your x value, or your domain. Those are kind of the things you'll hear me call that, all right? Also, we could say independent variable. These are all terms we use. A second thing for notation would be what f of x sub 1 means. That is a range member. Specifically, it's the range member that x sub 1 maps to. So we could think of this as a y or an output for that specific range member or a dependent variable. And of course, also we call it the range. So f of x sub 2 would be the range member that corresponds that x sub 2 maps to. So if we had our mapping diagram, I'm trying to make sure I leave enough space for other stuff. So if we look at that as a mapping diagram, or I won't call it 3, I'll just say as a mapping diagram now, I've got my domain, I've got my range, and this is for the function f. X sub 1 will map to f of x sub 1. X sub 2 will map to f of x sub 2, and so on. So I really want you to start thinking about this as being an x, but this as being a y. Like this is an x value. And you think of this, when you see this notation here, it really just means like a y value. Okay, so on a graph, it might look like this. If I say this is my x sub 1, and I have a point here, right? The y value, or the range that it maps to, we're going to call that f of x sub 1. Sometimes we just figure out what the number is. We'll say, like, you know, this maps to, like, if this is a value of 3, then that's a value of 4. But I want you to understand the notation. So that's one thing I think students come into calculus not knowing, and so I'm trying to get you ready for calculus. This trips students up. They see this notation used in several different ways, and they don't think of it simply as that's just a y value, and it really trips them up with stuff. So we're going to start doing some of that right from the beginning in pre-calculus, all right? So that's the stuff I wanted to say about function notation. Now we're going to look at what our definition of an inverse to a function is. Okay, so an inverse to a function is the relation obtained by simply switching the domain with the range. Now the thing is, I was careful to use this word, a relation. So you have a function to start with, but once you switch the x and the y, or the domain and the range, right, it may not be a function itself. So I'll call it a relation. So finding the inverse is simply switching the x and the y. It may or may not, now that new relation that's formed may or may not be a function. So it doesn't automatically have to be a function. I mean, let's go back to our example of blood type. If I switch the domain and the range, so now if I'm going to map the inverse relation and I go backwards, it's indeed not a function, because the blood type in this case, this example, A positive, maps back to two other people. So if that were my domain now, right? So for the inverse, the range becomes a domain. So now I have a domain member of A positive. It's going to map back at two different people. Therefore, it's not a function. This is why we can't use blood type to solve a crime. I don't know if Mr. Tong or Mr. DeStasio here is the criminal. Since they both have A positive blood type, and that was found on the scene, I can't say which one stole the laptop from Mr. Belanda's office. I can definitely say it's not Mr. Zucca, because Scott has A minus or A negative blood type. So you can rule out people, but in most practice, you know, using blood type is not really a good way to solve a crime. All right, because there's too many people that have the same blood types. So that's an example where the inverse is a relation and not a function, blood type. Okay. So let's move on to look at what a one-to-one function is. Okay, now that's going to be where the inverse is itself also a function. So I'm going to say it this way. A function is one-to-one. I can write it like that as well. You'll see me write it this way and this way. If no two elements in the domain correspond to the same element in the range. So again, let's look at our blood type. This is why I know it's not one-to-one, just looking at, if I get rid of this blue stuff, just looking at the function itself. It is a function because each domain member maps to exactly 1, but it breaks our definition for one-to-one. These two elements in the domain here map both to the same range element. And the definition says if no two elements in the domain correspond to the same element in the range. So they call it one-to-one. It implies that there's a one-to-one, like for every element in the domain, there's a unique element in the range. So for a one-to-one function, the example that I want to think of, first I want to say this in function notation, our definition. So using our function notation, I could say it like this. I'll make a simple conditional statement, an if-then statement. If you have two elements in the range and they're not equal, so this is like two different elements in the domain. I'm sorry, I just said range. These are domain elements. These are x values. If you have two x values or members in the domain and they're different, so they're not the same, then they must map to two different y values. They cannot map to the same y value. So remember that range or y value is denoted like that. So the y value for the x value sub 1 is not going to be the same as the y value for x sub 2. This is like using function notation or a mathy way or math symbol way of saying the same thing here. Okay? And in plain English, we're saying no two elements in the domain map to the same element in the range. Okay? So that's our mathy definition of one-to-one. An example, actually I want to do this. I'm trying to keep this stuff separated. An example would be a DNA mapping function. So if I take the same four people, we've got Jason, we've got James, we've got Mr. Zuka, and we have my wife, Christina. If I take the DNA function, I'll call it d of x. This is my domain. This is my range of d. Jason is going to map to Jason's DNA. I need a bigger circle here. I don't exactly know what my DNA sequencing is, so I'm just going to use function notation. It's d of Jason. So that represents whatever my actual DNA is. I don't know it, so I'll just write it like this. Okay, and then I can say James will map to a different DNA sequence. It's a fact. We have different DNA. And Scott has his own DNA. And Christina has her own DNA. This holds true to our definition, right? No two elements in the domain map to the same element in the range. Each domain member maps to its own unique element in the range. So that's why I can use DNA to solve a crime. So now if they found DNA in Mr. Blanda's office, we could probably link it back to who stole his laptop. All right, so because it's a one-to-one function. So I like this example of blood type versus DNA. DNA is a one-to-one function because for every domain member, it points to a range, and that range member points back to only it. It's a one-to-one correspondence, okay? So that is our definition. Those are our definitions that we're going to work with through the rest of this video. Oh, and the last thing I want to say is just remember that a one-to-one function, another way to think about it is a function whose inverse is also a function. Remember I said up here, it doesn't have to be a function. So that's another way to think of a one-to-one. I said the inverse is just a relation where you switch the domain and the range. So I've got a function, I switch the domain and the range, and it's still a function going the other way, then that's a one-to-one function. All right. So we're going to determine whether these relations are functions, and if they are functions, we're going to determine if they're one-to-one functions. So when you're given a set of points, I like to make a mapping diagram. So let's make a mapping diagram for f. The function f has a domain and a range, and the domain of f, 0, maps to the range member 0. I get that from here, right? This is my domain, and that's my range member, or you can think of x and y, right? Input, output. 1 maps to a range member of 1, and then it says lastly here that 1 maps to -1. So I already have 1 listed in my domain. I don't need to list it again. 1's going to also map to -1. So f is not a function. The domain member 1 maps to 2 different range members, not a function. I don't have to continue on and do part 2. Let's do our mapping diagram for G. G, if I look here, this says that -1 is a domain member that maps to the range member 1. Now I look at 0, 0. That means 0 maps to 0, And then I look at 1, 1. 1 maps also to 1. So that is a function. G is a function. So now if it is a function, we have to check if it's a one-to-one function. I'm going to say G is not a one-to-one function because I noticed that these two elements here in the domain map to the same range. Okay? They map to the same range. So that means if I went backwards, the 1 in the range maps back to, that's the inverse that I'm mapping, maps back to 2 different values. Okay? So if I wanted to, I could draw a mapping diagram for G inverse to check if the inverse is also a function. So I switch the domain and the range in the inverse. This is notation for inverse. I'll come back to that a little later. Okay? So G inverse is going to have 1 and 0 as its range, and its domain is going to be negative 1, 0, and 1. I took these values and made them the domain. I took my domain from G and made them the range. Okay? So now, if I follow the mapping, 1 maps back to negative 1 and also 1 in the inverse, and 0 maps to 0. So I can see that the inverse is not a function. So I'm going to say the inverse, G negative 1, is not a function. Therefore, G is not one-to-one. So there's a couple ways to check it. I can just say it breaks the definition right here because these two domain members map to the same range member. Okay? I just wanted to show you another way to think about it. H, let's check H. I've got my domain, I've got my range. I'm suspecting this will be one-to-one because the other ones weren't. Negative 1 maps to negative 1. 0 maps to 0. 1 maps to 1. There is a one-to-one correspondence, right? Each member of the domain maps to one unique range member. It doesn't map, they don't map to the same range members. They each have their own range member pointing back at them in the inverse. So I'm going to say H is a one-to-one function. And you could say because, and you would restate the definition. Each member, I'm not going to rewrite it out. I'm going to try to pick up the time here, but I'll pick up on time a little bit, go a little faster. So let's move on. So I would just say because each member, and I would finish the definition. All right, let's look at an example. How can you tell using the graph? So if I look at these and I want to graph these, we can graph them in Desmos. So let's go ahead and do that. Let's graph x equals y squared in Desmos. So I've got x equals y squared. We see that we get this sideways parabola. So I'm going to go back and sketch a graph. It makes a sideways parabola. So from the graph, is this a function? Well, I can look at, like, let's say this domain member C here. It doesn't pass the vertical line test, right? So we've got the vertical line test for functions. If a vertical line hits the function or crosses the function more than once, it is not, or crosses the relation, I should say, more than once, it is not a function. This breaks the definition of a function. The vertical line really just represents a single domain member. In this case, the vertical line represents the domain member C. So C hits the function, hits the relation twice. I can't call it a function. It's not a function. It hits the relation twice. So that means C maps to this y value, let's say H, and also K. So the one domain member C produces two different range members. If I did a mapping diagram of domain and range here, C would map to H, and C would also map to K. And that's not a function. So it fails the vertical line test. So therefore, this means therefore these three dots, not a function. Y equals x squared. I don't need Desmos to graph that. I kind of know that that makes a parabola like this. So I can't draw a vertical line anywhere that hits twice. So it is a function. So we're going to say it passes the vertical line test. So it is a function. So therefore it's a function. Now, how do we check if it's a one-to-one function? You could do something called the vertical line test. If I take an element on the range here, let's call it H, I can run a vertical line through here, and I see that it hits the function twice. So that means that that has two domain members, maybe A and maybe B, two x values that produce the same y value. So if I did a mapping diagram of that, right, domain and range, that means the domain member A would map to a y value of h, and the domain member B would also map to h. So if the horizontal line hits twice, that means it's not a one-to-one function because each member of the domain does not map to its own unique member of the range, right? We have two domain members mapping to the same range member, not one-to-one. So I'm going to say it fails the horizontal line test. Therefore, it's not a one-to-one function, meaning the inverse is also not a function. Then we look at y equals x cubed. I also know, I don't need decimals to graph that it looks like this. This will pass both the vertical line test and the horizontal line test. There's no horizontal line that will hit twice, so therefore this is a one-to-one function. First I had to check that it's a function. It passes the vertical line test. Then it passes the horizontal, so it's a function and it's a one-to-one function. All right? How do we do this algebraically? That's the question now. So here we're going to need that function notation definition of what it means to be one-to-one, which said if you have two unique domain members, then they must map to two unique y values or range members. They can't be the same. So if you remember from geometry, if this statement's true to be for one-to-one, then the contrapositive would also be true. Contrapositive means you switch the hypotheses and the conclusion, and you also negate them. So that means if I negate this, it means f, the y values will be equal. Then the x's should be equal. And what this is saying that if I have the same y value, then they better map back to the same x value, right? So if I look at a mapping diagram, if I have x1 and x2, and f of x sub 1 and f of x sub 2, if these are the same, right? So if I kind of merge them together and just say they're really the same thing. Let me draw a bigger mapping diagram, sorry. So if I say that really f of x, that wasn't much bigger, is the same, so they're really the same range element. What they point back to better really be the same domain element. Right? So that's how we can show that a function is one-to-one. We want to show that if we make the y values equal, then the x values have to come out to be equal for it to be one-to-one. So I want to show that one domain element is, one range element is equal to the other range. I want to start with that if. So that means f of x sub 1 means I would plug x sub 1 into this function. And then f of x sub 2 means I would plug x sub 2 into this function. So I take out the x placeholder and I put in what I want, x sub 1 and x sub 2. Now I start simplifying or solving this equation down. So if I add 2 to both sides, these cancel. Divide by 5 on both sides, these cancel. And I'm down to x sub 1 cubed equals x sub 2 cubed. So now to get rid of the cube, I can raise both sides to the 1/3 power. And you end up getting x sub 1 equals x sub 2. Since you showed that if the y's are equal, then the x's have to be equal, you could say the function is one-to-one. This is a weird one. It's like, what did I just prove? It seems almost obvious, but this is how you prove it algebraically, okay? So now let's try this guy. If I say the y values have to be equal, I'm going to set this up by saying I take my function, take out the x, and replace it with my x sub 1 and my x sub 2. So I've got x sub 1 here and x sub 2 here. I said, okay, if my y's are equal, let's solve this. Well, the first thing I need to do is you have to remember that when considering absolute value, what it really means is you might have the positive version or the negative version. That's what absolute value means. You have to consider both the positive and the negative of everything in the absolute value. So what we have here these are or statements, right? So really I have 4 combinations of 4 possibilities that I have to check, and I can really pare it down to just 2. And really I just need one to not work to show that this is not one-to-one. So I have four possibilities. I could say the positive of the left-hand side equals the positive of the right-hand side, or the positive of the left-hand side is equal to the negative of the right-hand side, and I can keep doing all those. I'm just going to pick one. So I'm going to pick the positive version of the left-hand side equaling the negative version of the right-hand side. So now when I solve this, I get x sub 1 plus 1 equals, I got to distribute this negative sign, negative x sub 2 minus 1. So now I can subtract 1 off both sides, and I get x sub 1 equals negative x sub 2 minus 2. So they are not, I'm not getting x sub 1 equal, whoops, I'm not getting this. So I'm showing that the same y values don't map back to the same x values. They're different. So I'm saying that x sub 1 is not equal to x sub 2, so therefore the function is not 1 to 1. That's how we show that algebraically. Okay, so now we're going to look at the inverse function specifically. We're saying now that the inverse is a function, that the original function is 1 to 1. So if this original function is 1 to 1, it implies that there's a 1 to 1 correspondence. Each member of the domain maps to only exactly one member of the range, and no two members of the domain map to the same range member. So that means like each domain points at a range member, and that range member points back at that domain member. There's no like splitting either in the domain or the range. So think DNA. Each person has their own DNA, and every DNA can point back to only that one specific person. I also think of our device program here at BHS. It's different than other schools. Some other schools might have a computer lab, like say Wisconsin, where the students come in and 5 different kids might use the same computer throughout the course of the day. So that's a function because each kid uses their own computer there, but then the computer does not map back to only one person. There's 5 different people that use that computer throughout the day. Period 1, someone uses it. Period 2, someone different uses that computer, and so on. At the high school, each student has their own device. That's why we call it a one-to-one program. It's actually a mathematical term for functions, right? There's a one-to-one correspondence. Each person has their own device, and that device is for that person only. It points back at only them. Okay, no one is sharing a device. Okay, that's called a one-to-one program. We're going to look at how this is denoted. So when the inverse is also a function itself, we call that the inverse function, okay? And it's denoted in function notation, f to the negative 1 power. That's inverse notation. This means something. It means that there is an inverse to f, and because it's in function notation, it means that it is also a function. It implies that that's a function, okay? So it's denoted as f inverse of x. So if we think about domains and ranges here, the domain and the range of the function f is mapped in green. So if we have an x value here, it maps to a y there. And then I'm going to look at the inverse. This is the domain of f, and this is the range of f. If I change colors to purple, f inverse would be the mapping of y back to x, and this would be the domain. The range of f is the domain of f inverse, and the domain of f is the range of f inverse. So you're switching the domain and the range as we said before. Is there anything else I want to say about that? Yeah, let's do a quick example. So I'll think of like the example of the function f of x equals 5x. That's a function. So that means this function maps any value x in the domain to a value of 5x in the range. So if I do a mapping diagram of f, it maps, takes a member from the domain, call it x, and it maps it to the range and calls it 5x. All right, so pretty simple. If we want to map backwards, so I'll do that in purple, right? If we want to do the inverse function, what would that function have to be to undo that and come back to the x? So what would I have to do to 5x to undo that and make it just x, right? So if we want to map or undo, so keep in mind that this idea of inverse functions, they undo each other. Whatever a function does to something, to a domain member, the inverse function undoes that. So we develop another function, and that function in this case will be, we can figure out what it is. It'll be multiplying by the reciprocal of 5, or 1/5 x. So that means if I take 5x and I multiply it by 1/5, the 1/5 times 5 becomes 1, and I just end up getting x. We use this idea, we've been using this idea since 7th grade. That's how you solve equations, right? If you have like 5x equals 10, we say, oh, we're going to multiply both sides by 1/5. We're actually applying the inverse function to undo what's being done to x. So it's the same idea here. So that's basically what's going on. If I use function notation, I could say something like this. The inverse, f inverse, undoes the function f to just get me back to x. So f inverse of f of x, well, f of x is 5x. So I can replace this, f of x, with its range output 5x. I didn't want a straight line there. So if I say f inverse of f of x, which is 5x, I can now plug 5x into my inverse function. My inverse function is 1/5 x. So if I plug f of x into f inverse, I end up getting just x. Right? So remember, I take this 1/5 x and I plug f of x into it. F of x in this case was 5x. Now it's got to work both ways. So if I take f of x and I plug f inverse into it, I should still also get back to just x. It should undo each other. So if my function, if I take my inverse function, or I should say my function 5x, it's 5, I got to plug something in for it. If I plug in the inverse function there, I know 5 times the 1/5 is 1, and I get just x, so it works out. So that's how you can verify inverse functions. Let's do an example. So if I say, if I have my two functions here, I'm going to go back to the green pen. I've got my function f and my inverse function, f inverse. If I want to verify, you've got to verify that when you do the composition of f into f inverse, you get just x. They undo each other, and you got to verify the other way. So they undo each other in both directions. So you've got to verify both. You've got to get down that you got to show that it equals x, that they undo each other. You need and. You got to do both. So if I want to show that f inverse of f of x equals x, I'm going to do that composition. So that means I'm going to take the function f of x and plug it into f inverse. So I'm going to start with f inverse. In this case, f inverse is 1/2 of x minus 2. So I take out the x, and I'm going to put in its place f of x, right? So we know f of x is over here. So 2x plus 4. Now, if I simplify, distribute my 1/2, I get x plus 2, and then I have minus 2, and then I simplify further, I just get x. So I verified that f inverse undoes whatever f is doing to x. Now I want to verify that f undoes whatever f inverse is doing. So now if I start with the outer function f, that's how I do compositions. I write it down as 2x plus 4. I remove the x, and I put in its place the function f inverse. Whoops, that's minus 2. I simplify by distributing the 2. I get x minus 4 plus 4, so I end up getting x. So that's how you verify that functions are inverses. You have to show both of these things. You have to show that f inverse undoes f, and f undoes f inverse. That's how you show it algebraically. So we're going to do this for one that has a domain restriction. For instance, I know x squared is a parabola, but if we restrict the domain to only the positive x's, it looks like that. So that's what f inverse looks like. And the square root of x I know looks like that. So it looks like it could work out. They both pass the horizontal and vertical line tests. So let's verify it algebraically. So I want to say that f inverse undoes f. I want to show that it just equals x. So f inverse is x squared, and I want to plug f into that. So I go grab f, which is the square root of x. So I'm going to see that the square root of x squared is going to just equal x. And that's for, all our positive x's. X is bigger than or equal to 0. And let's do the other way. So that's check. We show that part. We showed that. Now we got to show the reverse way. F of f inverse of x equals x. So f of x is square root of something. And then I got to plug f inverse into that. So f inverse is x squared. So then we square root the x squared. We end up just getting x. if our x's are always the bigger than or equal to 0, right? So we don't have to consider the negative versions here when squaring and square rooting because we've restricted the domain to be only the positive x's or 0. So we don't have to worry about negative x values here. So we showed both directions, so it is verified. That's the end of the video. This is about the length they're going to be, anywhere from 20 to 40 minutes.